So today we're going to talk about magnets. So to start off with, we have this slide here, and so it says magnets, electric currents flowing in a wire create a magnetic field that surrounds the wire. So that is a new fact that you probably didn't know. And this is why electricity goes right after magnetism, because they're so intimately related. So we talked about, current flowing through a wire is essentially just electrons flowing through the wire. Well, it turns out every individual electron, they have a mass. Electrons also have charge, but they also have what we call, the actual term is intrinsic magnetic moment, but I'm just going to say they act like tiny magnets. I'm just going to call them tiny magnets. Turns out protons also act like tiny magnets, but the proton tiny magnet is like 1,000 times smaller than the electron one, so we don't even have to worry about those. So if you understand that the electrons kind of have like a tiny magnet, it kind of makes sense that like when you start flowing them through the wire, well, then the wire will have a magnetic field whenever a current is flowing around it. Now, this magnetic field isn't very significant unless you get a lot of current flowing. But that explanation of why magnetic fields exist around a wire isn't a very good job of explaining it. Because to really understand it, you need to understand special relativity. And there's a video later on these notes that I'll have a link for, and I'll tell you guys, like, hey, if you want to understand more about this particular fact about, current flowing in a wire creating a magnetic field, that video will do a much better job. But I don't want to get too much into it because we haven't really talked about special relativity. We'll talk about that later in the year, but that's not really something to approach right now. But so suffice it to say, electrons have a magnetic field, and that's why they're going to create a magnetic field when they pass through a wire. But again, if you think about something like an actual magnet that you see here in the picture, well, everything has electrons, so theoretically everything could be magnetic. That's true, but most things aren't. And so that's what we're going to spend most of this class on, is talking about how some things can be magnetic, but most things aren't, even though they're all made of these electrons. So before we go much further, let's kind of review a couple of things here. So those are our two objectives today, those two questions down there. It says, why do compasses point north, and what makes a magnet a magnet? Mm-hmm. But before we get to that, let's review two facts that you guys should hopefully know. Number one being that if you have two magnets, like pretend like these are two magnets, you have a north pole and a south pole, right? And if you put the norths together, they repel. If you put the souths together, they repel. But if you put a north and south, well, they attract. Okay, that's the first fact you guys should know, that opposites attract, likes repel. Okay. The second fact that you guys hopefully know about magnets is about compasses. And so compasses are actually just tiny magnets. And if you have your compass, it will point north. So the north end of your compass points north. So our question is, but why do they point north? Because if you take those two facts back to back, opposites attract, likes repel, and your compass points north, that doesn't make any sense, because if you look at this picture here, the north end of the magnet is the red part. And the red part of the picture, do you see how the compasses are pointing away from the red part towards the silver part? That means these tiny magnets, these tiny compasses, are actually pointing to the south pole of the magnet. Well, I want to give you guys one additional fact that you guys really should know. And it's clearly demonstrated in this picture here. This fact that you guys should know is that, well, the Earth acts like a magnet. I feel like you guys knew that. But let's focus on what's written in blue here first. So it says right here, geographic north pole, geographic south pole. That is exactly what you guys know about the Earth. And so the geographic pole is the points around which the Earth spins. Okay, that's what makes them the north and south pole. That is not revolutionary. Okay? What you may not have known is that the magnetic poles are probably opposite. So here, notice in green it says south magnetic pole, and then in red it says north magnetic. So there's a couple things that you guys should notice. Is that first of all, the south magnetic pole is near the Earth's north magnetic pole, and vice versa. And they're not in the same spot. They're close, but they're not in the same spot. So the first thing you guys have to realize is this should make perfect sense with those two rules that you should already know: that opposites attract and like repel, and that your compass points north. Here you can see the compass is pointing towards the north pole of the Earth because they're attracted to the magnetic south pole. Because if this diagram here was not true, what that would mean is that your compasses wouldn't point north. Because you guys know, you have a compass, the north end of your compass points north. But that seems contrary to our rules of opposites attract and like repel, because if the north geographic pole was near the north magnetic pole, well then the north end of your compass would point south, which it doesn't do. So I want you guys to take a second to digest this information and, just really look at it. Because I feel like it makes perfect sense and it doesn't override anything that you guys already know. Just, I feel like this is one extra piece of information that the magnetic south pole is over here. So here it talks about why this is, and essentially the Earth's core is made out of iron, and because iron has a lot of free electrons, and iron itself is actually a pretty good magnet, which is what we'll talk about in a minute. But as the Earth spins, it creates this magnetic field. And you'll notice that the poles aren't in the same place, like the magnetic pole isn't the same place as the geographic pole, because even though it's caused by the spinning, you can see these field lines here. And these field lines look all nice and straight, but that's just a diagram. In reality, the field lines are tangled and twisted. And they're tangled and twisted because the Earth spins faster than the field lines do. And because the Earth is spinning faster than the field lines drag behind and they start to get all tangled and twisted. What that means is when they're tangled and twisted, it will in turn push back on the core of the Earth and cause those poles to move around. So first of all, the geographic poles are everything that you've always known. They don't move. They're solid. That's the point around which the Earth spins. But the magnetic poles move daily over time. They don't move very far, maybe 1 or 2 centimeters per day. But over time, that can move pretty far. And so they just kind of wander back and forth because they're being pushed by the tangled field lines that are out in space. And so here's a fun fact that you guys may not have known. You guys hopefully learned in history class about people sailing across like the Atlantic Ocean in like the 14 or 1500s. And you're like, oh, well, they did it with a compass. And it's like, yes. But what you may not have known is they knew back then that the magnetic pole was, first of all, south pole is on top. And they knew that they weren't in the same spot. So they actually have log books where it shows the location of the ship, like daily. And it shows the location of actual north, the geographic north. And then it also showed the location of the magnetic south pole. And because of these books, we can actually use these books that the sailors used to use, and we can recreate where the pole was. And we can actually map how it's wandered over time. And so it wanders around. And because the thing is the compass works, if you're just going from your house to the grocery store and you happen to know that, the grocery store is due north of me, compass will get you there. But if you're going an actual distance, like across the ocean, these two being in the same, or not being in the same spot, is a real problem, and you will never make it. So that's one of the things that, like I said, we've known for a long time they aren't quite the same spot, but you may not have. So I just want to take a second for that. Here, the slide talks about these magnetic field lines a little bit more. And so if we just have a regular magnet, we say the field lines go from the north pole to the south pole. And one of the other things that's not clear here is that it looks like the field lines stop at the south and begin at the north. That's not true. They just go completely around. There's no beginning, no end. Just like And current in a wire would have a circle around it, so this magnetic field would just have no beginning or no end. These field lines go through the magnet itself, because if you take this magnet and you cut it in half, you don't get a north pole and south pole. You'll get two smaller magnets, each with north and south poles. So when you're looking at that, you can cut a magnet as many times as you want, and you'll just get smaller magnets. They won't be as powerful, but you just simply get smaller magnets. And that's because, again, it really comes from the electrons, and the electrons themselves act like tiny magnets. So these field lines just go all the way through the material. All right, so these next couple of slides, we're getting into that question of what makes a magnet and why other things are not. So I'm going to go through these slides pretty detailed, but there's a video right here that goes through it goes through basically the same thing that's on this slide and the next couple, and it really does a good job of explaining why a magnet is a magnet. So if you don't like my explanation, hit that video and it'll give you a different, it's the same explanation, but from a different perspective. So first of all, we have a thing called ferromagnetism. All right, it says right here, materials that are strongly attracted to a magnet and can be magnetized are called ferromagnetic. Usually we don't say ferromagnetic, we just say magnetic. We leave off ferro because originally ferromagnetism was named after the first element we knew was magnetic. That was ferrium, or iron. Iron is the namesake of ferromagnetism, and so if you weren't aware of that, if you look up iron on the periodic table, its symbol is Fe, because ferrium is the Latin name. So, and again, here it gives you the gist that magnetism on the atomic level is really due to this little intrinsic magnetic moment of the electrons. And we'll get into that in a second. So the reason why we don't typically say ferromagnetic anymore is because there's basically 4 elements that at room temperature can be magnetic, and they are iron, cobalt, nickel, and gadolinium. And it's just those 4. So if it was just iron, maybe we would still use ferromagnetic, but generally we just say magnetic. There's actually several different types of magnetism. There's 5 different types in total. We're only going to look at ferromagnetic types of magnets. The other ones are just kind of weird and rare. It's like finding out there's like a 5th or 6th state of matter. Like, yeah, they're over there, but that's beyond the scope of this class. So here, this thing starts off that says, okay, basically, you've got electrons. Okay, electrons are magnetic because they have a charge, a mass, and a tiny magnet part. So all electrons have that, just like all protons have that. We already said protons we can basically ignore their magnetic moment because they're so small. So you might ask the question, why is it? Why do these things have this magnetic moment? I don't know. Why do they have charge? Don't know. But because they do, these are the results. But you'll notice that not everything has not everything's magnetic. Like this pen I'm holding in my hand, it's not magnetic. So how come, if everything's made of electrons and electrons have a magnetic field, how come not everything's magnetic? Well, there's essentially 4 different things that need to happen for something to be magnetic. Okay, so the electrons are magnetic, everything's got that. But what happens is when you put things together, so it says right here, most elements whose atoms have magnetic moments. So it kind of skipped a step here. So you have electrons which are magnetic, but they may not make magnetic atoms. So that's the first step, getting a magnetic atom. How do you get a magnetic atom? Well, it just kind of depends on how many electrons there are. So there's 2 things that can happen to the electrons. Electrons can pair up, and if they pair up, they usually pair up one magnetic moment up and one down. And so you have like a north pole, south pole pointing up, and the other one points down. And so in that pair, their magnetic moments cancel. Or you can have electrons that are orbiting your nucleus, and like current in a wire, they will also produce a magnetic field. But if you have one going to the left and one orbiting to the right, then those orbital magnetic moments will tend to cancel out. So the only elements that are even available or the only atoms that are even available to make a magnetic atom are the ones that are near the middle of the periodic table. And if you look at a periodic table, you'll notice that like iron, cobalt, nickel, like those are right there in the middle. But you also notice that there's a couple others like right below it or right next to them that should also work, but they don't. And the reason for that is because the next level is when these atoms get together, and that's what this is talking about. When you're trying to form a solid, there's different ways for these solids to form. You have your magnetic moments like this right here, or that it's just kind of a mess. Well, each of these atoms might be magnetic because of its electrons, because they're only in a half-filled electron shell. But because these atoms decided to stop, align like this, there's no overall magnetic moment because they're all just pointing in random directions. So that's one possibility. Another possibility is they all do line up like an iron. And the last possibility is that they line up opposite to each other, just like the electrons did. And so like cadmium, you'll notice is right there. If you're looking at a periodic table, it's right there near iron. It should be magnetic, but it's not because its atoms decided to line up opposite. And so that's what this is talking about here, that you got to have a half-filled electron shell. You have to have the orbital magnetic field not canceling out that. You've got to have the atoms aligned. And then here, this talks, again, if they all happen to line up, okay, you can get a magnetic poles that line up. But here's the other problem. As this level is what we call like the domain level. And so what ends up happening is that a bunch of atoms, as you can see here in this picture, all of these atoms in this local region lined up. But in the region next to it, they lined up together, but they lined up differently. And so overall, the whole thing doesn't have a magnetic field because each of these regions are not aligned with each other. Like they're aligned, like the atoms are aligned, but this group of atoms is not aligned with that group of atoms. So again, you have no magnetic moment. So if you have all of these things, you got to have obviously electrons are magnetic, but the atoms have to be magnetic, and then the solid crystal structure has to be magnetic, and then the domains also have to align. So if you get all four of these things, then you can have a magnet. And so some of the iron we dig up out of the ground could be a magnet. But you can still get iron that's not a magnet because of mostly this, because the domains aren't aligned. But it turns out that if you have a bunch of domains that are not aligned, you can expose it to a large external magnetic field and actually cause those domains to expand their influence and then start to magnetize the whole structure. And if it's a large enough external magnetic field, you can force that other material to become a permanent magnet. Okay. Here, there's a video here about printable magnets. And essentially, this is a kind of fun video. You don't need to watch it, but it's a fun video where they talk about some new technology with magnets. And if you watch the video, it is really weird what they're doing. But again, it's fun. You don't need to watch that for material. And that brings us to electromagnets. And again, electromagnet is probably just a piece of iron or something like that that's not magnetized by itself. But again, if we pass current through a wire, it will have a magnetic field. Well, if I wrap that wire around my iron and then I turn it on, well, now I have that magnetic field in the wire, which then forces those domains in the iron to align. So now I have a very strong, what we call electromagnet, and it's one that I can turn on and off. And so you can see here in this picture, you can see that wire here running. It would actually have current in it for your electromagnet. And so that video there is, again, another fun video, but it's about, the strongest electromagnet on Earth. Next slide. So here, this is what I mentioned earlier. I gave you the fact at the beginning that current running through a wire will have a magnetic field. I said it's because of the electrons. That's generally what this is, but here, this first video talks about exactly why that is with a better explanation that, like I said, I'm just not going to go into now. The only thing I would ask you is like, why does this thing have a magnetic field? It's because of the electrons, whether it's a permanent magnet or electromagnet. Now, like I said, there's more detail to those explanations. And I went through the detail for permanent magnets. I'm not going to go through special relativity right now because that's something we'll cover in the future. So I'll wait to cover that there. And then here, this is the second video is just another fun video about MRIs. So it's a magnetic resonance imaging machine. And it should be noted that the magnet in this video is only about 4 Tesla. So Tesla is our unit for magnetic field strength. So in this second video here on the slide, the magnet is about 4 Tesla, and that one earlier on the electromagnet slide, that one is a 45 Tesla. So this will show you how dangerous MRIs are if you have metal around them. And so if you can imagine that's dangerous at 4 Tesla, a 45 Tesla magnet is ridiculous. And then we have a couple slides here. This one talks about a motor versus a generator. Basic gist of this is that with a motor, you put in electricity, get out mechanical force. With a generator, you put in mechanical force and get out electricity. So they're opposites of each other. For a better explanation, watch that video. If you don't know what a motor versus a generator is, watch that video. It's very important. And like I said, I could draw all this stuff up here, but I'm not going to be able to draw it very well. They have a good animation of a motor versus a generator. But if I gave you a picture of a motor versus generator, well, here's a motor and a generator. But if I gave you a more detailed picture that talked about like the pieces to tell them apart, well, the motor has a source of electrical power, like a battery, whereas a generator will have a source of physical power, like this gasoline motor, or like a handle, like a windmill turbine. That's physical mechanical force, and we create electricity. And then last slide here talks about transformers. No, not those kind of transformers. We'll talk about transformers that step up or step down our voltage. And it uses a thing called electromagnetic induction. And so here it shows you pictures. So here you can see this gray transformer, which will be up on the power poles in older neighborhoods. And you see these green boxes. Those contain transformers as well, which you typically find in the newer neighborhoods. And the way a transformer works is it's just 2 coils of wire connected by an iron core. And so the whole point is to step up or step down your voltage. So what you're trying to do there is when you send power through a line, a very long wire, it will have a little bit of resistance, and so it will take some voltage to push your current through the line. So if you're trying to push something, let's say like 100 miles, well, that's going to take a certain amount of voltage. So let's say it takes 1 volt per mile. Well, if it's 100 miles worth of cable, it will require 100 volts. Well, if we only have 120 that comes out of the wall, and the power company sends you the voltage at 120, you're going to lose 100 volts before it even gets to your house. And 20 volts is simply not going to be enough power to run your appliances. So what do? Well, we send it through the power lines at a much higher voltage, because if we send it, say, at like 100,000 volts, it's still going to cost 100 volts to push it through the line. Because of that, we'll still lose that 100 volts no matter what we do. But 100 volts out of 120 is most of it, whereas 100 volts out of 100,000 volts is basically nothing. And so we get a lot less power loss if we send it at high voltage, which is what we do. But you don't want like 100,000 volts coming out of your wall. Well, that's what the transformer's job is we can step them up to a higher voltage if we need to, or step them down. So like these 2 pictures here are step down transformers. And that's what they're used for. They probably don't have 100,000 volts in them. They probably don't have 1,000. Maybe they step it down to like the 120 for your house. And the reason why they don't have like the 100,000 is you will also see, out on the road somewhere, kind of depends on where you live. Like here at Geyer, there's one literally across the street. It's a power substation where they have really high voltages. They're like 100,000. They go into the power substation, and the power that comes out is only at like maybe 1,000 or 10,000 volts, which is a lot safer to go into your neighborhood. And then that stuff will get stepped down again by these more local transformers. So the important thing about transformers is that they're not electrically connected, they're magnetically connected. And so transformers only work with AC. They do not work at all with DC, which is why Even though 90% of the stuff you guys use, like your computer, your cell phone, I can't even think of it, but pretty much anything that uses a battery, your car, uses DC, but we send all of our power through AC because it's very difficult to change DC voltage. We just need a transformer to change AC voltage. It only works because it's changing that magnetic field with time because the current's changing with time. So that's it for the notes. So hopefully you guys got something out of that. And y'all have a good day.